How's it going, guys? In this video we're going to continue on with reaction rate problems, and in particular we're going to do rate order in this video. So this is going to come in handy for, it's kind of like a cheat sheet for all these types of problems. That's like the general format there, rate equals K times the reactant and then to the M. And so K is the rate constant. Anything with a bracket, that's going to be the concentration of reactant, and then the M here is going to be the order of the reaction. And these are kind of the general structures that correlate with those formats. So for these reaction rate videos, what I'm going to do is I'm going to use these same three problems, and then in this video we're going to do the order determination, and then in the next video we'll do the rate constant, like we'll calculate K, and then in the following video after that we'll do reaction rate initial, like we'll calculate the initial rate based on changes in some of these variables. So first off, let's jump into the first one here. And I think I'm gonna, like usual, I tried to make them increase in like difficulty and complexity as we go here. So for this first one here, consider the reaction A yields B plus C. The following data was collected experimentally, and then there's four little lines there, and what it's going to ask us is determine the reaction order. And in this case, it's saying, you know, the reaction order M. Pretty straightforward. There's only one reactant, so we're only looking for the order of that one in particular. And here's how we're going to do it. So first of all, start by writing the expression. So in this case, it's, you know, A yields B, and that's like the general format it follows. So for that, we'll say that the rate is going to equal K times the concentration of A to the M. That's like our basic structure. Now what we're going to do is compare our two concentration pairs. So we're comparing some data from these, and you can choose any two or whatever in it, and it should work out okay. But we're going to plug it into the formula. Rate 2 over rate 1 is equal to concentration 2 over concentration 1 to the M. So let's look at these here and kind of try to decide what we got there. This is what we're eventually trying to solve, but first off, let's break it down a little bit more. So if we're choosing two of these, we'll sub in, let's say 0.76 over 0.34. And in this, I believe it is significant that the rate 2 or the rate 1, whatever's the rate 2 should be of the greater concentration. I'm sorry, of the higher rate, which often will correlate to the higher concentration. And let's see, so we have that equal .24. Now we're going to compare concentration 2 to concentration 1. So we get 0.30 over 0.20. It's going to equal 1.5. And that was our, so MS, and then this is theoretically like M. So now what we can do is we can plug into this formula here. What we're going to do is we're going to take, so we have the 1.5, and then for the concentration it's going to be 1.5 to the M. So if you can't tell, you just log both sides. So like if you can't tell what it's going to be. So basically in this case we have, sorry, I should have written this out a little neater. 2.24 is going to equal 1.5 to the M. So that's what we've just derived, and this will allow us to get our answer. From there, like I said, if you can't figure it out, just by looking at it, because a lot of times you will be able to. You just do this. Log of 2.2 over the log of 1.5, 2.24 equals, you're going to get 0.342. And then on the bottom, what do we get? 0.176. And we'll divide that out. Equals 1.943. We can say that is about 2. And because that it's close to the number 2, that will give us second order. So essentially, I don't think we're going to take this problem any further from that, but basically what that means is that we've solved for m. So this problem is, the rate of this is k a 2 for second order. But it didn't ask for that anyway. We just threw it in there. All right, cool. So let's keep moving, move on to the next one. Let's see here. All right. Okay, so consider the reaction A plus B yields C plus D. And then the following data was collected experimentally. We got some data there, and we're going to go from there. So A plus B right here, it's going to correlate to this type of structure. I mean, you know, like that basic formula. So let's see. First thing that we're going to do is look at comparing concentrations. In this case, when you have multiple, it's pretty important which ones you choose to compare, because your answer can be different depending, and there is a right way to do it. So in this case, what we're going to do is looking at the concentrations that change specifically, and we're going to compare the ones that change. Because obviously, if you compared 0.1 to 0.1, there's no change, so it's going to be 0. But as we can tell from the entire data plot, or you know, the whole data set, it does at some point change. So we're basically going to calculate it based on the change to see how much it changes, rather than, you know, isolate the part that there is no change. So here's what we're going to do. For A, we're going to compare the trial 1 and 2, because for A it goes from 10 to 20. From 2 to 3 it's 10 to, it's 20 to 20, it's no change, and then it's the same change from 1 to 3. But we're kind of planning ahead there, because, you know, it looks like you can't do 1 and 2 for B, but you know, that's something that you gain with practice. 0.1, 0.2, so we just have those two, and we'll compare the difference. So how do you go from 0.1 to 0.2? Multiply by 2. And now we're going to compare the corresponding rates. So we have, what do we have here? 2.0 compared to 7.9. How do you go from 2 to 7.9? So we'll say that's about 8. That is going to be times 4. And now what we say is 2, we take the 2, and we say 2m, 2 to the m is equal to 4. So what exponent would you raise 2 to get 4? It's going to be 2. M equals 2 equals second order. So for A, it's second order. Now, for B, again, we're going to compare the ones that compare the trials that change. That's the significant part here. So what changes? Again, from 1 to 2, it doesn't change. From 2 to 3, it changes. So we'll go from 2 to 3. So now we're doing from 2 to 3. We have 0.1 to 0.2. Again, that's times 2. And then we have 7.9 to 16.1. which again, if we kind of do a little bit of rounding, it's going to be about times 2. So here's what we got. 2 to the m equals 2. So what power would you raise 2 to get 2? It's just going to be 1. Anything to the first power is just itself. So what we have is m equals 1. It's first order. So now what we know is, here's the rate. The rate, and again, like I said, we follow this formula. We just solve for m, and in this case n, which is the m of the b, the second. It's going to equal k of a, and we solved a as to be second order, so we'll put that there, and then b is 1, and there's no need to raise it to the first power. It's just if there's no number next to it there, it's just we're going to assume that it's 1, it's first order, so it's not contributing to the order, so to speak. So that will be kind of our answer there for the rate we're solving, and first order, second order. All right, cool. So from there, we'll jump into the third and final one I had prepared. And this one, like I said, it kind of is supposed to increase in complexity as we go down down the ways here. Okay, so consider the reaction BrO3 minus plus 5Br plus 6H plus yields 2Br2 plus 3H2O. The following data was collected experimentally. There's a ton of zeros there, but don't let that throw you. Just keep in mind we're looking for the difference. We're looking for the changes in terms of comparison. So look at which trials to compare. That's the first thing. As soon as you look at as soon as you get the problem, I think the first thing that I would start doing is look for a pattern, see what changes where, and plan ahead, because sometimes you can use multiple comparisons for one but not for another, and you don't want to spend 5 minutes like working forward and then realize you have to go back and do something over. So let's kind of like look at them all. So for BrO3 minus, we know the only change is for the last one, so it probably makes sense to compare something to the trial 1, 2, 3, 4, 5. So yeah, start with for the BrO3 minus, what we're going to do is we're going to take trials 2 and 5. So we're going to say 0.0220 goes to 0.0660. So what is the difference here? It's times 3. And then we'll compare the relative rates. 1.41 times 10 to the negative 2, and we're going to 11.28. So what do we got there? That looks like it's roughly, so like in these cases when you're trying to figure out reaction order, a lot of times you're going to do a bit of rounding, and so in this case we'll say like say that's 11. You could say that that's 12, or you could round it down to 11 and say that that's 1, whatever you wanted to do. In this case, what I did is I just divided it, and what I got was pretty close to 8. So for 8, we're going to say, or for this one, we'll say 2. I'm sorry, so we have 2 and 5. I'm sorry, that was not 8, it was 9. 9. So we have 3 to the m equals 9. And usually it should work out. I mean, I think at least in my experience, a lot of the times it ended up being that it was pretty close to a whole number that you could pretty easily do in your head. You wouldn't get like some ridiculous decimal or something. But in this case, it's pretty clear that m is going to equal 2. So it's going to be second order. And then we'll move on to the next one. For, let's see. Okay, so what we're going to do is for Br, comparing 3 and 4, because that's where there's another change from 0.0125 to 0.0250. and it looks like there's no change on the other two, and there's no change on the other two for H+. And that's just that, you know, it helps you be more confident in your answers. 0.0125 compared to 0.0250. This is times 2. We'll compare those rates, 1.41 to 11.28. So in this case, what would make sense is, so let me see what I got here, 1.41. Okay, I see what happened here. So this one, when I was comparing these rates, the 660 rate is 12.70. That's why I was getting my my number mixed up here. So that was 9. This one was 8. So we have here the 2 and the 8. So we're going to do 2m equals 8. So what power would you raise 2 to get 8? It's going to be to the third, because 2 times 2 is 4 and times 2 is 8. So what we're going to get is m is 3, and this is the third power. Third order. All right, so now lastly we can end with the H+ concentration, and for this one we'll check out where does the change happen. It changes between 1 and then from 1 to 2 and so on. So what we'll use is just 1 and 2. I like to always do adjacent and consecutive rates if possible. In this case, you could for these two, and it didn't necessarily make sense to for that one. But you know, because this one we were looking for the biggest change in rate over here to get the most accurate answer. If we compared these two, we'd get a much lower order. I mean, you know, it wouldn't have worked out the same exactly necessarily. So H+ we have 1 and 2 for 0.0250. We're going to compare that to 0.0500. We know that that is going to just be times 2. Now we'll compare the rates, 1.41 times 10 to the negative 2, and I'm just checking to make sure that the rate, like the times 10 to the negative 2, they're all times 10 to the negative 2, because sometimes they'll be like 1 times 2 to the negative 3, and then you got to do things a little bit more carefully. But 1.41, we can compare that to 1.42. So I'm comparing 1.41 to 1.41 because the only change that we could use is one where the rate doesn't change. So this is really just times 1. So if you even need to go this far, we have 2m equals 1, m equals 0. So for H+, it's going to be 0 order. And what's really significant about anything that's 0 order is what that basically means is adding any amount of H+ to this reaction will not speed it up in any way. So it's of 0 relevance to the reaction in a sense. So if you're asked to write the reaction rate for this, or the rate law formula, we're going to have rate equals BR O3 minus to the 2 because it's second order. Then we have BR to the third order, and then H+ to the 0 order. We don't indicate if it's first order, but in this case we're indicating that it's 0 order because we don't, because if there's nothing there, you're going to assume that it is first order, which it's not. And that would affect, how you solved out for it. Now, this is the way that you can also write it. You won't be wrong to write it this way. Just completely omitting the H+. Because like I said, if it's 0 order, it has any amount of it won't affect the speed of the reaction. So either of these answers can be correct. So yeah, hopefully this was helpful. Going over the rate order and how to find them. Like I said, we're going to kind of do a series of videos here where we're going to use these exact same problems. So like theoretically, you could, a lot of open response questions will have you do first find the rate order, and then like calculate K, and then do what is the initial rate at this and this metric. So from there, I just wanted to segment them out so anyone could focus on any individual. If you are only stuck on one of those calculations, then you can do the whole video on that. But yeah, just continue on to the next video if you want to keep going with your reaction rates. Hopefully this was helpful to someone.